Hello guys, back at again. Don't know that's the correct sentence. Actually, I can't give the disclosure for every video. So this is not a. I'm just going to briefly say this is not a tutorial intended to be a tutorial, but you can use it as. But everything I said in this video is not. I'm not a maths expert. I'm just trying to learn this subject. So bear with me if you're watching this. And I try to explain as simply as possible to for those who are listening to this. Uh, yeah, and I'm doing this. Another reason is to improve my English. So sorry for that if you guys can't if I my sentences not no didn't don't make any what do you call mm, any doesn't if my sentence doesn't make sense, I'm sorry about that. So I will try to make it better as we go on. So let's jump into it. So first thing we discussed in the first video about the introduction, why maybe we use this we develop this algebra or linear algebra or abstract algebra to algebra. Yeah, that's so first I'm basing this on the lectures done in my university. So the most of this knowledge come from my professor Tilaka. So uh, I should give credits where it's due. Uh, so this is not my knowledge. I'm just collecting his knowledge and other reading other books and web and uh, collecting it here. So let's go. First, I'm going a little bit talk about. Let's get talk about vectors. Vectors. This is still an introduction, but I'm going to a little bit of depth. Then I'm going to a topic which regards to this. This is not a topic. I'm just talking about vectors. So we know we use vectors mainly in physics, but also it's a mathematical model, but object, but we use in physics mainly to let's say we can use vectors to indicate position. If this is coordinate axis, is there is an object in 3 2 coordinate, we can say let object there is an object at 2 3 coordinate, right? Sorry, not 2 3 3 2 coordinate. In physics we can use position vectors. We used position vectors to identify that and said let's say this is v vector v. We usually denote vectors using underscore sorry underline or bold letter. So bold in letters in using when we are writing is hard, so I'm going to use underlining. So vector v is, there's a lot of way to write it, right? So I can use what do you call, I write the same thing, right? 3 2 3 2 using round bracket or parentheses, or I could use angular brackets. It doesn't matter. I think actually it is just a convention we are used. So if I want to define a convention to write this, uh, I could write like this, but it's not a very useful way of writing, right? So I'm going to, for the sake of this series, I'm going to stick with this convention, which indicates using angular brackets. But you will may as you may will I don't know what's what of this word. Let's say let's it. Oh, I lost it. You may well as use, oh okay, something like that. Parentheses also. So I'm going to use this. So we can denote this vector as 3 comma 2 within angular brackets, right? So let's say that object moved uh, 3 units to north, right, parallel to y-axis, right? So this would be, so 4 units, let's say 3 units, this would be 5, right? 3 units would be 5. I could write this vector, let's say denoted w. I could write w as no x displacement, just 3, right? Right. I know the new position of the object is same, can be represented using the last dark green arrow, just I just draw. Let's say this is u, vector u. I know that this vector is 3 comma 5. This is 3 and this is 5. I don't know you whether you can see my cursor, but I think little bit you can see. Let me try to do something about it. Uh, yeah, now you can see, right? So sorry about that. Okay, so if I look at this, I can see that 3 comma uh, 0 plus 3 is 3, 2 plus 3 is 5. So if I write like this, v plus u w, I can write like this, right? The 3 comma 2 plus 0 comma 3, which is equals to 3 comma 5. So the object vector hold this kind of property, this type of property, right? It can be added. We say this is a, what do you call, a operation. This is operation, right? Since this is done on two objects, on the objects, this is called a binary operation, right? uh, when we talk about, and so looking at this, we can define binary operation plus, let's say this is called plus, as this: if a is a vector which has component a1 and a2, then b is also a vector which has components, let's say this is a components. I know I don't going to define everything about vectors because we already know about those. So I can define a plus b is 1. This is b1 and b2. We can define it as a1 plus b1 comma a2 plus b2. We can divide it like this. Also, if I know this is our real numbers, right? So it can be what you call commutate without changing results. So it could be a b1 plus a1, b2 plus a2. So I can write this like a1 b1 minus b2 b comma b2 plus a1 comma a2, right? So if I summarize this, I can write a plus b. Isn't this b plus a, right? Yeah. So we can write b plus a, which is equal to a1 plus b1, a2 plus b2. So I can define this bind operation like this, and it has commutative property. But if I get let's say this is a two-dimensional vector, which let's say we have a three-dimensional vector. Let's say p1, p2, p3, and q. q1, q2, q3. If I can, vector multiplication, we usually call this is cross product. I know p cross q, which is a long definition, but fact is that not equal to q cross p for cross product for three dimensional in R3. R3 means uh, set list of the list of real numbers with length of 3. This is not equal, right? So which means not every binary operation plus is commutative, but not every binary operation might be commutative. So we need to define something. Need to define. We need to abstract this all. Then now we only talk about vectors, right? So if I get a matrix, which is also a influence for this bit of this field, let's say vector A, matrix A and matrix B. Don't think about the inner workings or inner dimensions of this matrix for time being. Just let's say this is two matrices which has same dimensions matrices. So if we know a plus b is b plus a for matrices, that's a fact, and we can use that. But for matrices, uh, a times b not equal to b times a. So this is not commutative. The dot or the multiplication vector multiplication is not a commutative uh, of binary operation. So we have to generalize this broad field. So we first start small. Now we are coming to a topic, the main topic, first main topic of this what you call subject or module. Oh, thank God. First one is groups. Now we are going. We are starting from the beginning and try to achieve vector addition multiplication, matrix addition multiplication from multiplication from starting from a generalized form. The first generalized form is a group. This is just a name. This is just a name we define to a specific set of for a set which follows a specific amount of definitions we introduce. So let me be clear. Let me explain you about it. Maybe that's not clear. It's not. I think it's not very clear the way I said it. So let's say we can say there's a group G. We use G as a group. This is a group. G is a group which is set. G could be 0, 1, 2, or G could be -1, 6, 5, or G could be let's say real numbers, so a sort of real numbers. G could be set of quotients, so there could be anything, right? So if G is a group, okay, if G is a group, if and only if, which means if G is a group, following rules will follow. If following rules will follow, G is also group. This is a definition. We are defining group to be this thing. So first one is G is non-empty. We can write this in mathematical notation. G is not equal to empty set. If G is empty, we don't have anything to talk about. So it's kind of obvious we need to have a empty set. Second one is we need to have a binary operation. So we this is group is defined on a binary operation. So we need, if G is a group, is not very clear about the binary operation, so we are going to write is G comma star or asterisk is a group, right? So asterisk is a binary operation. This is a very, what you call a generalized binary operation. Asterisk, this is binary operation. This could be plus, minus, division, multiplication, or maybe square root. I don't know. It's not a binary operation. Sorry, not square root. Power, a to the b power, or integral of fx from a to b, a b being the objects. This could be anything. So we generally use this asterisk, since we don't use asterisk for any other binary operations we generally use. So these all are occupied for different meanings. So avoid confusion, we use asterisk. But using asterisk may introduce some confusion later on. This is a double-edged sword, I think. So yeah, it could be binary operation. First thing is, this is an empty. If we take element from this G group, G set, let's say for all every element on uh, G, I take two elements a comma b, which is element of G. I take two elements from G. I didn't specify a and b not equal. So there can be a set G only has one element, but a and b could be the same element. So if I take two elements from G set G, the binary operation, which is asterisk. This could be plus, minus, division, multiplication, power, anything. So uh, should be also a element of G, which implies I write it down the wrong way. First, I need to write the description, so don't worry about it. I just want to say just the binary operation is closed. Closed mean when you get two objects from the G set and you do the binary operation to those objects, you get another new object which is also included in G, right? For example, if I take real numbers, right? I take real numbers as the group G and binary operation as plus. If I take two real numbers from the set, I can say 1 and 0.2, these are real numbers, and I do the binary operation, I get 1.2. 1.2 is also a real number, so which means the binary operation is closed, which is again which means when you do a binary operation to two objects in the same in the set G, it will produce another object in the same set. Third one. Oh. The next one is associativity. This is a binary operation, as we already know. Therefore, this binary operation can only take two operands, or what you call objects, at a time to do operation on. So if I'm going to do binary operation on three objects, we need to group them, not in the definition of the group's sense, but just we need to categorize them uh, to groups of two to do the operation. So if I get three objects, I say ABC, which is in G, and I first do B time B and C binary operation, and then I do uh, the result with do the binary operation results with the result and the A. which must be equal to eta A, binary operation B, and results will be binary operated again with C. This is called associativity. Should be associative. Otherwise, this could be very hard to build a model around it if we the order if the order matters, right? So we define group to be group to have associative property. Otherwise, there will be very little set of sets that uh, follows that follows. We're going to hard. It's going to be hard to build a definition around it and subject around it. Maybe I don't. I that's what I think. This is not the fact. So I just as a disclaimer again. I'm not an expert. I'm just saying things that I came to my mind, coming to my mind as I'm talking. Yeah. Then associativity. So example, for example, if I'm going to take the g as the real numbers again. If I take 1 and 2 and 3 as three numbers, we know that and binary operation is plus mm, uh, 1 plus 2 plus 3 is equal to 1 plus 2 plus 3, which is equal to 6. It's a fact, right? So if it has proven and we all know that. So associativity might should be a what do you call fulfilled to be a group, right? Fourth one is there exists a element, right? There exists a element. I just say E. Let's say E, right? Uh, in idea of elements or something like that, or identity element or something like that. There is a exister E, which is a element of also which also element of G, which is the set we took. And if we do a operate and we take any other element from G, there's only one element in G, and if I take that element and any other element from G and I do the binary operation on those two, regardless of the order, I get the number I took to do the operation. So we call this element is identity element. Identity element. This is similar as if I take example, if I get I'm going to going to take the same example again and again. If I get in real numbers, the identity element is 0. So if I get any a number and add this with 0, which is equal to 0 add into its a, it is equal to a. Number is not going to change adding this element. So we call this element in the set is called identity element. So if G with binary operation asterisk is a group, there must be a identity element which satisfy this property. No, there should be identity element, which means identity element is this which satisfy this property. And the last one is there only five. The for all a in G, which means I take any G from the set G, so any a from set G. For each one, there exists a bar. I also in G, which means if I take a means any element from G. That for that element, for any element I pick from the group G, there also exists a bar or a inverse. We call it a inverse, which in binary operation with binary operation a with binary operation a bar and a bar with binary operation a, which produces uh, the identity element, which we call this element a bar inverse in sorry so sorry about my writing. I'm just inverse, right? Inverse element. So that's it, right? This is the definition of a group. This is very arbitrary definition, right? So this definition is on Earth done by humans, right? So if some alien find out about abstract algebra or linear algebra, they might have different definition, or maybe they don't have abstract algebra at all. So this is a definition constructed by humans. This is not written in nature or something like that. So this is basically human construct, right? This is a definition of a group. So and this definition is not the only definition of a group. You can see that this generally group have these properties, which are but closed under binary operation, associativity, and identity element. There exists an identity element. Every element has an inverse, and set is non-empty. So we can encapsulate these properties into many other types of definitions. We don't have to use these exact five definitions, but generally, uh, general consensus is that a group have these properties. But definition might be different from book to book, or lecturer to lecturer, or teacher to teacher. They might have different definitions. So this is the definition I'm going with. If I'm going to prove something, I'm going to use these definitions. If I assign to prove something is a some set is a group under some binary operation, I'm going to use this setup. You can see that there is no commutativity on this five set of rules, right? Definitions. uh, there is only commutativity in identity and inverse element, but other than that there is no commutativity, which means a plus a asterisk b equals b asterisk a. This is not in here because it's harder to achieve, right? Not every, as I talked earlier, this is not every object has binary operation with some objects has that property. So specifically we define uh, that as a what do you call another definition, right? So I'm going to this is going to be a definition of abelian group. This is abelian group. So this is just an extension of groups, including the commutativity of the binary operation. Mm, so we don't need. So we are going to uh, define it like this: G with the binary operation asterisk is a group if and only if what is a not just a group, my bad, it's an abelian group, it's an abelian group which is an abelian group, which means it is a first it has to be a group, is a group. Then additionally we give the commutativity for the binary operation on the set. So for all a and b in set G, any element, if I take any element from set G, we say a with binary a with b, sorry, a binary operation with b equals b binary operation with a, which means commutative binary operation is commutative. That's the definition of abelian group, just extension of definition of group. So we may well have used uh, abelian group definition only, but uh, as we going forward, we are using this definition. So let's see what we can do with these definitions. Ultimately, we don't care about definition. Actually, we don't need definition to do maths. Maths is built to make things easy for humans, do calculations, do various things. Basically, maths breathe our build our civilizations to this point, right? As much discovered, as calculus discovered by Isaac Newton, the huge progress on human civilization has started, and then in nearly 400 years, right? uh, we were able to achieve so much more than we were ever were able to achieve in the history of humans, in the million years of history, if human civilization. So yeah, so this is not about definitions or ultimately, right? Ultimately, it's not about definitions or something like that, but we need to have basic good foundation to build upon. So basically, at the end of the day, you just need to have knowledge to do binary, not binary operation, do things with vectors, matrices. Basically, we most use those objects. uh, yeah, that's the main goal should be, not remembering definitions like that. But it's good to know definitions, and it's provide us a solid structure and foundation to build upon. So that's the basic of it. I'm going next time going to, it's been 30 minutes of this recording, so next I'm going to do is do some problems, or not problems. Math is not made to give us problem, it's just made to make human life easier. So but unfortunately, in this the study system or the education system the world driven on is based on assessing our skill. So they need to some way to assess our skill. So they came up with a solution called examinations, so which is include questions. So we just have to do them to understand and get a better grasp of everything. So in next video we're going to talk about do some examples and problems about groups and abelian groups, just a little bit discuss. So see you there.